But until now, we did not consider waves. We described just oscillations. But when we have a function which describes the harmonic oscillations, we can easily find the function which describes a simple plane harmonic wave. Waves propagate oscillations in space. So for a plane harmonic wave propagating in just one direction, z, we can simply write this again. Real valued cosine on the left and the complex exponent representation on the right. Here z is our single coordinate and k is called the wave number, which is defined by the speed of the wave propagation and its angular frequency. And again, on the right, you can see that we can easily extract the phase of the wave into the multiplier. Now, let's recall the state we discussed in the beginning of this episode. As we remember, this state plus is actually a superposition state, and it can be considered as both 0 and 1 states implemented simultaneously. The state 0 corresponds to the photon which oscillates in the horizontal axis, while the state 1 corresponds to the photon oscillating along the vertical axis. In the state plus, both these photons are in phase. But what if we consider this state? It looks pretty much the same as the state plus, except that for the vector 1, we now have a slightly different coefficient, imaginary unit instead of real unit. Does this substitution change our state? Let's see. Though photons are not themselves harmonic waves, they can be represented as a sum of harmonic waves. So here again, for the sake of clarity, I use only one harmonic wave of some angular frequency omega for each photon. Photon 0 is described by this function, and its real part is just cosine omega t minus kz. And it oscillates along the x-axis. Photon 1 in our state is represented by this function. And we can see that it has a relative phase shift by pi divided by 2. So its real value is going to be sine omega t minus kz. Let's see what happens here. Let's put our state in the point where z is 0, to the beginning of the coordinate system. Then, if t is also 0, we have the position of our oscillation on the x-axis at point 1, since cosine of 0 is 1 and sine of 0 is 0. Now, when omega t equals to pi divided by 2, we have the position of oscillator at the y-axis at point 1, since sine of pi divided by 2 is 1 and cosine is 0. When omega t becomes equal to pi, we have again the x-axis, but the value of our function, the electric field, is on the left. It's minus 1. With omega t equals 3 pi divided by 2, it is again on the y-axis, but in point minus 1. And with omega t equals 2 pi, we close the period and return to the initial point. It appears that this state, 0 plus I1, defines the state with rotating polarization. And the rotation is counterclockwise. And since we have a counterclockwise polarization, we can easily define the clockwise polarization simply by changing the sign before the vector I1. These two states are orthogonal, so they also form the basis in the state space, and they can be used for photon polarization measurement. The device we would need for such measurement is called a circular polarizer, and you can easily buy this thing in the photographer's shop.